Hello friends, this video will give a short description and brief idea for foundation designing in RCDC and availability of different features for the design of foundations. So on the screen we can see the four topics that will be covered in this video regarding the design of foundation. Here on the screen, we see a footing module which is open in front of us for the footing design. In the column layout, this is the column layout which corresponds to the column numbers as per the analysis file which is imported in RCDC for footing module. Similarly, this is the input data. This is the analysis or the node number from the analysis file, the column mark, the footing type, which we have over here is a four type: sloped, step, pad, and on draft footing. The column offset from the towards the footing for the first step, and the raft thickness if you're designing it for a common raft. Let's go to settings and general design settings. Here we have three parameters which will have its implication on the sizing for the footing. Here we have gross SBC. Gross SBC is the net SBC plus the overburden pressure, but the footings can be designed without considering the overburden by just unchecking this box. Also, we have the surcharge load, which is the additional load that can be considered for the design. Next, we have three checks. There's a check for buoyancy, check for sliding, and check for overturning, by which the foundation that is designed can be checked against all these three parameters. Then we have provide top steel option. Either we can do it for all the footings or we can do it for a specific foundation depth if the foundation depth is say above 600 or 750 anything. Then we have provide face reinforcements, that is as per the user requirement or the footing design considerations. Next we have the net SBC, in wherein we have to input the value, say we input 300 kilonewton per square meter. Also we have a very beautiful feature available over here which is varying SBC, in front of which we have a set option. So this form is now open for us, wherein we have to just input the varying SBC values over here for L by B ratio and the as the width increases, and for the particular L by B ratio as the varying SBC changes. So let us for now consider the net SBC for the design. Then we have these basic parameters. Next we come on to the cross section design, wherein these are the three features or the three options which are available for the design of the cross section. One is the average pressure method. Let me just show you in the diagram how do we calculate the average pressure for the shear design. Let me explain you FC11. So when we are considering average pressure method for calculation, if we want to calculate the average pressure along the 1500 mm side, what RCDC will do, it will calculate the maximum of average pressure of P3 plus P4 or P1 plus P2. So the average of maximum will be considered for the further design purpose. Similarly, when we are calculating the average pressure along 1800 side, what RCDC will do is it will calculate the average pressure of P1 and P4 and P2 and P3 and consider the maximum of both, and the maximum will be considered for the final design. Maximum pressure will consider the maximum of the pressure which amongst the four corners of the foundation, and factored SBC is we will consider factored SBC for the cross section design. Also we can change this factor, it can be edited manually. Let's say it is 1.75. Then we have permissible loss of contact over here, wherein if the footing is supposed to be eccentric footing, we can either design it as an eccentric footing and also avoid loss of contact by up to 50%, from 0 to 50. Then we have these concrete grade, steel grade, cover, live load reduction, and all these other settings. Over here we can see the plan limits and the set option button available over here. Okay, this is a important feature which is used to apply or input the value of eccentric distance for which the column will be eccentric. So before starting the eccentric footing design, let me just briefly explain you how do we input the value or the numerical value for the eccentricity. For for a column to be eccentric from the left edge, we can put an offset left from the left side, which will go up to the face of the column. So if a column is eccentric by say 500 up to the center, then we would just reduce the column half the column size from the required eccentric distance. Similarly, this will be applicable for applying eccentricity in any direction. This is the left offset, this is the bottom offset, right offset will be from the right face of the column, and the top offset will be from the top face of the column. Also in the displayed diagram, we see four pressures P1, P2, P3 and P4, wherein if we select cross section design as average pressure, then the average of pressure calculated at P1, P2, P3 and P4 will be considered for the design. If we consider maximum pressure, then the max of P1, P2, P3 and P4 will be considered for the design. And the third one is the factored SBC, wherein the factor of SBC which is applied will be multiplied by the net SBC, and that will be used for the cross section design. So in line to the diagrammatic explanation of giving the input of offset along x and y, say if the column has an offset of 750 along the x direction, then there is no offset for y direction. We will just input the numerical value of offset eccentricity along the x direction, say OK, and over here we'll just confirm all the settings. I have already selected the load cases and load combination. Let us design this as a pad footing. This we can design as a stepped footing. This can be done as a sloped footing, and this can be done as an on draft footing, wherein the raft thickness is minimum of 300, and we can also change it. Let's keep it 450 and let the column offset be 50. So also before proceeding ahead, we have an option to change the or insert the eccentric distance from here. Just by right click we can set the planned limits. Here we have the maximum, we have two options for setting the maximum offset, in local direction and in the global direction. Let's choose to put the input in the local direction. If I say for C5, I input it as 800, or say let's keep it same at 750 and just say OK for that. Similarly, we can input it from here just by a right click. We can say set plan limits, and in the similar way we can input the eccentric distance from here. Now we will redesign the footing and check the results of all the settings or modifications or the parameters that we have set for designing the footing. Yeah. So over here this has become an eccentric footing in the x direction, which it has gone to the right. This is the stepped footing. This is a sloped footing. This is an on draft footing. And this is a too much of eccentric footing, wherein let's reduce the eccentric distance. I'll say design. I'll go to the design settings. I'll go to set and I reduce the distance. The higher the distance I input, the lower will be the offset, the lower will be the eccentricity, as explained in the diagram. So by just increasing it to 900 the design of the footing is now 2450. Now let's accept it and we see that yeah, now the footing has again become a concentric footing rather than eccentric. For column C1, if we want to just reduce the size, what we can do is go to redesign section. Let us allow the loss of contact to be up to 10%. Say OK and redesign, and let's check how much the size is reduced. So previously it was 8350 by 8350. Now it is becoming 7050 by 7050, and the depth has also reduced. So let's accept this. and check if it's clashing with something. No. So now this footing is an eccentric footing, this is a stepped footing, a sloped footing, and an on raft footing. Let's just go to the reports and see the detailed drawing. FC1, 2, 3 and 4 we'll see in plan, section and along both the directions. I say mark PCC and all the things. I say okay. So the section that is developed over here, this is the plan for FC1. These are the sections 1 and 2. We have 3 and 4, 5 and 6, 7 and 8. So 1 and 2 is for the eccentric footing. This is section 1 1. The footing is now eccentric. So the distance that we had input is the distance from the right face of the column up to the right face of the foundation. The distance we had input was a positive distance. Over here we see this is plus of 650. If we input it as minus of 650, the footing would become eccentric from the left side of the foundation. We would check that also. So this is the eccentric footing. This is the section along which the along x, that is eccentric, and along y it's not eccentric. So the footing is at the center or symmetric along y direction. Then we go to the stepped footing for section 2 and 3 and 4. I'm sorry. So 3 is this section and the fourth is this section. Similarly, we have section and plan for a slope type of footing and an on raft type of footing. So now let's just check if we are inputting the value for negative value for the eccentric distance. I say set and just input it as minus 650 and redesign the footing for that distance. Let's see. Then footing size is now increased from 7050, the 7050 to 7250. Let's accept this design. Yeah. So now we see for a negative distance, the footing becomes eccentric on the left side of the footing. So over here, a quadrant plays a role wherein the first is plus plus, second is minus plus, third is minus minus, and fourth will be plus minus as x comma y. So this is with the eccentric footing. Then we also have pressure check report. Let's check it for these three foundations itself. So this is my pressure check report. I can just extend this. This is my design for table C1, wherein I can see my analysis forces, the eccentric forces, wherein P is multiplied by the eccentric distance to to calculate the mxx, including mx plus p into the eccentric distance. Similarly, myy is calculated the total weight, which is downward p plus the effective self weight. The soil pressures, max soil and the minimum soil pressures over here are calculated. The SBC increase that we had given, and this is the loss of contact percentage which is displayed. We had given a maximum loss of contact for this footing to be 10%, but the utilization is only of 1.72 and 1.58 as required. And this is the factor of safety for buoyancy and overturning along B and along L. Similarly, we have design of pressure for other columns. Let me just quickly show you how we can see the checks of buoyancy, sliding and overturning in the design calculation report. When I go over here, this is my general data for the footing, including the maximum permissible offsets which we had given as an input to the software, and these are the other soil parameters or the bearing capacity and other parameters. The design of cross section method by average pressure. The footing type is pad footing with an eccentricity. Okay, so here we have the maximum soil pressure calculation, the minimum soil pressure calculation, and then we have corner pressure calculation as P1, P2, P3, P4. Then this is the point of zero pressure which is measured from the uplift corner. And these are the further calculation done in the same regard. Here we come for the check of buoyancy, for which the critical load combination is considered as this and the factor of safety is this. So here we calculate the actual buoyancy and the permissible buoyancy. Same we have overturning along width and along length of the footing, and we check for sliding too, right? So this is all with the design of foundation and different features which are available for the design of foundations. Thank you. Let us quickly go through the pile design for a structure in RCDC. Here on the screen we see a file, analysis file, which is imported in the pile cap module for its design of pile cap and pile configuration, confirmation or consideration. We go to settings. In general settings, we have a small table over here or a form over here wherein we have to input a few data that is required. We have permissible pile numbers availability up to 6, from 1 to 6. When we select 1, 2, 3, 4, 5, 6, the list will be, number of piles will be 1, 2, 3, 4, 5, 6. When we select only 3, 4, 5 and 6, the list over here will reduce up to 3, 4, 5 and 6. So depending upon the permissible pile that a user has to allow for the design, the list will be displayed or considered. Then we have to give a pile number. Say 750 is the pile diameter. Then I have the design options wherein I have to give a factor for the capacity design. That is, if I say 1.5 times the capacity should be considered for the capacity design. Then I have check for pile shear check. I can, if required, or if there is a requirement of considering the overburden pressure for pile design, we can consider this, or else we can ignore it. We have provide top still option, provide phase reinforcement depending upon the user requirement, and it also depends upon the design criteria or the design considerations. Then we have pile capacity reduction, which can be 0 also. Then we have pile overloading, this is a 10%, and pile group overloading is also available, which can be 10 or say 15. Let's keep both as 15 and 20. Then we want, this is applicable for the detailing purpose. So pile numbering is required to be continuous, or it has to be column wise. Say for a column C1, if the pile numbering is P1, P2, P3 and P4. For column C2, if the piles are 3 and we want to number it as again P1, P2, P3, then we can select column wise, else it will be continuous pile numbering. Then these are the other design parameters that are to be set for the pile design, like we have the concrete grade, steel grade, the bottom cover, the top or the side cover. These are the default values as per the code requirement or the code specification. One thing to be noted over here is the pile cap offset which is required, and the pile spacing, which is by default 2.5 percentage. So over here we accept these changes, and we have a pile capacity table over here wherein we have to input the pile diameter and the corresponding compression capacity, tension capacity and the shear capacity for the required pile depending on the soil condition or the soil profile. Also we have to select the basic load cases, which I have already done, and basic load combinations are already selected for the design purpose as well as the sizing purpose, I say, and just keep it on the auto run. So first time we run any file in pile cap, the pile configuration or the number of piles required for a column will be set. So this table will display the pile configuration for a column, the corresponding pile cap, and it will display the pile configuration. If we have an option of 500, 600, 650, everything, then it will consider the required pile. Let us check that first. We will input the pile capacity for say 500 and 600 too. We will consider these two. So for 500, let it be 750, and this will be 75, and let this be 500. For 600, let it be 825, let this be 80 and this be 600, and I say okay. So when I run it for the first time over here, so the required pile is considered. So before auto designing it, let us first go back to the general settings and select the pile diameter. Let us first select it and check for 500 and say OK and redesign or auto design. So these are the number of piles for 500, 600 and 750. So this is 3 500 number of piles. This is 4 500. This is 4 500. So as per the required list, it has selected the number of piles. If it's 500 diameter, the number of piles is 3. For 600, it's 3. And for 750 also it's 3. Here if the requirement is 4 500, then for 600 diameter it will be 3 600, and for 750 also it will be 3 750. So we can select any one of the both, but for now the pile diameter selected over here is this 500. Now for this pile cap, say C23, which is this one, the numbers is 6 and 500 was not fit for this pile cap to be designed, hence it has considered 6 number of 600. So from the available list of pile diameters, it has considered the optimized or the most smallest or the actual required pile diameter. Now once again when we auto design it, we will get the actual pile configuration, actual design output for a pile cap, and we can see over here that only two diameter of piles are used, that is 500 and 600. A pile marked with this type will be 500 dia pile, and a pile marked with this type will be a 600 dia pile. So this is the pile cap layout. This is the design output for a pile cap. Now when we go to reports, let's just first go through the pile layout. So this is the pile layout that is generated. This is the distance between the center of the column to this pile. This is the distance between the two vertical distance between two piles and the horizontal distance between two piles. In this way, the horizontal and the vertical distance between two piles is reflected in the pile layout. Next in reports, we have the text schedule, which is vertical and horizontal. Let us select a vertical type text schedule for the pile cap. So over here we have the pile cap mark, the column mark, the piles that is required, the dimension of the pile cap, and the reinforcement for bottom and top, and the stirrups if required, and the side face reinforcement. So we have it for all the pile caps that are designed. Next we have a detailed drawing. Let us see a detailed drawing for 3 piles along for the plan section along L and at B, and just accept this and check out the detailed drawing for the pile cap. So along with the pile cap layout, here is the actual pile cap layout. We have a plan for PC1, then we have section 1 along X and section 2 along Y. So along X we have two number of piles, the column and the pile cap layout detail, and for section 2 again we have this pile and this pile which is far seen. So we again have two piles which can be seen in the section. Similarly for 4 piles, the pile cap plan, the section along X and Y is generated. Next report we have is the design calculation report. Let's check a design calculation report for a triangular type of pile cap and a square type of pile cap. Over here, this is the regular nomenclature. This is the general design data. Then we have the number of piles, pile diameter. This is the pile cap offset as per the user input given to the software. Then this is the pile spacing. This is also an input to the software. This is the pile size, pile cap depth, and pile cap weight, which is calculated. This is the maximum load on one pile calculation and load on the pile group, the maximum shear on pile group, and check for the uplift load on pile if any, Then we have the regular procedure and the calculation for a pile as well as a pile group and a pile cap. This was for the triangular type pile cap. Next we have for a four pile cap, which is a square pile cap. However, it can also be a rectangular pile cap. So quickly, just when we go through, we have the same checks and the same considerations of the pile design and the pile cap design for a single pile, for a group of pile, and for the entire pile cap. Next in the report that we can see is pile capacity check and sizing, which is really interesting to see. Let's see PC1 and PC2 again. So this is the pile capacity check and sizing, wherein we have a tabular format. Let's extend this so that we can see it on the same screen. Here we have a design table for table column C1, wherein we have the analysis forces. This is a total force, maximum load on pile and the maximum load on group pile. And then we have the shear on the group of pile. We have no tension on any of the piles. The permissible shear capacity and the pile capacity. This is a increase factor, and these are the other general design parameters that are considered and a pile or a group of pile is checked for. Then we can also generate a BBS. We'll just select two piles and say generate BBS for this. While the BBS is generated, wow. So over here we see the actual spacing and the presentation of the rebars in the pile cap. This is the bar mark, and this is the bottom face reinforcement plan. Similarly, we have a top face reinforcement plan for PC1. This is the section 11, which is along X, and both the bottom top bars, the side face reinforcement is shown over here. And we can see the BBS, which is generated for the element PC1, that is a pile cap 1, and all the bar marks along with the radius of bend. The summary of the BBS is given over here for the bar diameter of 10 and 20, the total weight that is calculated, and the total length that is calculated. So that's all about the pile cap design, the pile configuration that is considered, and the other design parameters that are considered for the design of the same. So let's hope that this video is really useful for the users to start with the pile cap and get used to with the pile cap. Thanks guys.